Welcome to week 3 of the course. So we've got actually today's lecture is the last one in our little sequence of essentially linear systems and signal processing kind of things. And we'll start looking at CT and how the actual physics of CT imaging works, probably was the last half of this lecture. But before we get there, we're going to look at some of these questions came up in the earlier lectures was, how often or how, fine do we have to sample something in order to sample it sufficiently? And this will lead us to something called the Nyquist criterion, which is just like the Fourier transform, something you should carry around for your life, right? It'll be useful in many endeavors. Okay. So to start out, uh, all of the signals you've experienced in your life, I'm fairly confident, have been digital signals as opposed to analog signals. In the old days of sound recording, like we discussed before, you used to have a groove on a vinyl record, and that was an analog signal in that it had a definition at every, point. And so if you have some signal here, this red line is our signal. Say it's a voltage that's changing as a function of time, and you have a value at every time point for that function. That's a continuous or analog signal. And, you know, old time electronics, that's what they used to use. Voltages were continuous and stuff like that. Now, what happens normally with a signal is the signal itself is sampled at some sampling rate or frequency, and the continuous signal is replaced with a set of numbers, right? And so instead of having to have this continuous signal, you could write down a function and say what that continuous signal was. You just carry around in your pocket this set of numbers, and that's your signal, right? And so when you stick you guys don't even know this, when you stick in a CD into, you probably do, right? When you're little, you had CD players in your car or something. They were still around probably when you're little. Um, so you put it in there, and on that disk is just a sequence of numbers, right? And just literally a sequence of numbers. And those numbers are fed in to a device that converts the number into a waveform, right? And that's why I can get so many darn songs on one CD, because you can, get so many numbers on one CD, right? So that's now in medical imaging, the whole thing now is digital. It used to be there was a continuous sampling in that there was film, there was light flashes in film, which you could consider a continuous thing, unless you get right down to the crystals that change their form to create film to go dark. But now virtually every detector is just a sequence of numbers coming out the back of it, giving you the waveform. So if we look at an example image, this is a CT image. It has 512 by 512 pixel values on this field of view. And each value can normally it's like 16 bits or something, it's encoded, something like that. So it might be plus or minus 32,000 would be the integers that you would encode as brightness on this thing with those 16 bits. And it looks pretty continuous when you look at it this way, because the individual values are very close together in space, right? And that we're displaying here. As we zoom in, you can start to see a few details which are interesting. One is you kind of appreciate the random noise in a uniform background. So this is blood in the left atrium. This is blood in the ascending aorta. And that blood should all have the same Hounsfield unit, should be the same number. It obviously isn't the same number because of noise processes. And so we have this variability here. But the other thing for this lecture we want to look at is we zoom in even farther and we take a look at the really fine details of this structure. You can see once we zoom in to this level, you can see they're boxes, right? And they have a finite dimension. Okay. And in this case, these boxes probably have a dimension of 0.4 millimeters or 0.38 millimeters, something like that. And each box has a brightness. And so when you look at your picture, you say, well, that's kind of weird. It has this boxy pattern. It's like a Lego set that I've built this image with, right? So if you're going to look at your image like this, you actually don't want to display these boxes, right? You want to have a finer sampling of that function such that you're not distracted by the fact you have discrete numbers and these boxes. This very well may be the highest resolution you can achieve is the distance between two of these boxes. But you shouldn't display it like this because obviously there's structure there that isn't in the patient, right? And so you should increase the number of points that are used to display this image such that it looks like that, right? Now we haven't increased the spatial resolution of the image. Two dots that you're not able to separate them don't all of a sudden become separable with this display. But what you get rid of is this undersampling of the picture itself, right? So whenever you're going to do some analysis for an image, pick your pixel dimension to display that image such that it's just the underlying function. It isn't those crazy boxes. The crazy boxes, though, do give you a kind of an idea of what your spatial resolution is. And it's a very lazy way of telling someone your spatial resolution. You could say, excuse me, sort of what's the distance between this pixel and the one next to it that's down, a certain value. And that's the interpixel distance in this image. And you say, well, it's like 0.38 millimeters. So that's sort of an estimate of what the spatial scale is of the resolution that we're dealing with. But we all know, because we're good engineers, that that isn't the spatial resolution of the imaging system. The spatial resolution is given by the point spread function and the modulation transfer function. Either one of those, right? Not by the voxel dimension, right? You should match the voxel dimension such that it makes sense. So if we draw a line through the image in which we are kind of don't have enough pixels to really represent the shape that well, you can see the image starts to take on this sort of stepwise gradients. And then when I fill in and use more pixels, that's the function that's under there when I sample it again. And that's more likely closer to the truth, right, of what's underneath. Right? So that's a really simple gestalt for what it means to sample an image. Like what's the frequency at which we're sampling this picture, right? And so mathematically, so that's okay. Mathematically, we need to describe how we're going to sample both the image, say, and sample in the Fourier domain of that image. And if we recall back to the functions that we sort of learned in our little toolkit there, one of them was a set of delta functions separated by some distance, right? So we had that, we called it a comb function or a bed of nails function. And so here's an example. If I have delta x, here looks like almost a centimeter or more, and I put a sample here, 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 and they're evenly spaced all over the object. That's one potential sampling of that object. It's not a very good one, right? Because we're going to miss a lot of details by skipping over all of this between samples. So we probably, if we're going to sample that function, we probably want to make delta x a lot smaller, right? So we bring it all in. And so this is halfway to smaller. Now we're at sort of a half centimeter. But we want to go down probably to, 0.25 millimeters or something to sample things at a high enough rate, right? So the mathematics of the process of sampling, it's simple, but there's a lot of algebra and terminology gets in the way. But if you have a continuous function, so let's go back to this thing. Let's pretend that we don't even have pixels under here. This is our continuous function, and we want to sample it, right? So that's our thing we're trying to sample. We can take one of those rectangular sampling grids and encode values of that function as a function of, grid point, as it were, along there. Okay, so this is a discrete function. This has discrete values for m and n, and it has, amplitudes at each one of those values. So that's something you can put on a computer, which is very convenient, right? We call the discrete sampling of that function is the continuous function at the precise values x and y that are given by this, m times delta x, n times delta y, okay? And so these are the sampling periods, okay? The inverse of the sampling period is called the sampling frequency. So it's how many samples per centimeter do you get, as opposed to how far apart are my samples in centimeters, right? So one's the frequency, and remember, it's samples per centimeter. That sure sounds like a spatial frequency in the Fourier domain, right? If you have samples per centimeter, it's a frequency. Right? So we're going to see how that works out, how we set that. How are these sampling rates set in imaging? For CT, it's pretty simple, right? We build a detector, remember, and if we're going to sample rapidly, this detector is fixed in place, and we have little bins that are each integrated across that bin as one sample, right? So right now, when I look at this, I'm already at a discrete sampling method. I have picked my sampling rate by picking the separation between these bins. Most CT scanners, 99% of CT scanners in the world, the distance between each one of these little sampling units is about 1 millimeter, okay, on that order, right? So you have this array of detectors that are separated by 1 millimeter in theta, which is this direction, and in z, which is this direction. So over generations of CTs, instead of rastering the source across the sample, we use a single source that has a fan beam coming out, and so we can instantaneously sample all of these projections. And the distance between each one of these is still about 1 millimeter. And then in the modern CT scanner, you stack these things on top of each other to get a 2D sampling grid. Yeah. This one here. Mm-hmm.
So you can sample by using like the comb function, right?
Correct.
Using like the direct deltas at different shifts
Mm-hmm.
explained by the signal.
Yes.
How is this different from that by using like rectangular sampling? Are you like
this is
like
the same?
Oh, okay.
Yeah.
Yeah, okay.
This is the same. So as we get into the math of figuring out what the Fourier transform of this thing is, we'll see it is just sampling with those Dirac deltas that are separated by some distance.
Okay.
Yeah. Okay, so that's our fundamental sampling rate in CT is set by that detector, right? You can imagine there is a push to make the sampling rate higher, right? So you could detect higher frequency or sharper edges and things like that. In CT, the problem with just continuously making more and more samples along your detector is that eventually you run out of photons for each spatial unit, right? So you have to have them big enough that you get enough photons to get a reasonable measurement. Secondly, remember in the current CT detectors, there's a flash of light which needs to be contained inside the box. To contain it, you need some septa that reflect the light back and forth, so you lose efficiency. So as you put more and more samples, the ratio of area that's sampling versus septa basically goes down, and your efficiency goes down. One manufacturer I think I'll show you some examples when we get there. Basically took a plunge and said, we're going to make twice as many detectors on our sampling detector. So they had something like this that was 1 millimeter by a millimeter. And they said, you know what? We're just going to go all the way to 0.5 millimeter by 0.5 millimeter. So they essentially doubled it in this direction, doubled it in that direction. That's a lot, right? So it's 4x times the number of, you know, signal lines coming out, the number of amplifiers, all of the technology. So the cost goes way up too. So it has to be worth it. So this is what the geometry looks like in the scanner we have here. This is from it's called the Revolution CT from General Electric. The tube is up here. It makes a fan beam of X-rays, and then it hits the detector down here, which has this sampling rate along there. And when you break open that detector, it looks like this. We have theta in this direction, and so it's going to rotate, around this way. So it's going to rotate in that direction. This direction is Z, right? So the patients on a table, you slide them in, and that's the Z direction or slice direction here. And then you can see there's chonked in here are these units, and inside each unit, we have all of the sampling detectors for that band. If we look, we're going to open this up right here and look at these sampling chips right here. This is the anti-scatter grid, and these are the sampling chips. And when I look at that, this is what it looks like. Anti-scatter grid lifted off for this illustration, and then here are the sampling chips. Each one of these panels has like 16 by 32, 1 by 1 sampling elements in it, right? Yes?
Limits for getting high frequencies. The second one being that flash has reflected in the detector.
Yes. So you want if you don't have the flash isolated to the detector and the photodiode, if there's a little bit of bleed around there, then you're sampling at a kind of a wider sampling value. It used to hit film, and now it hits a photodiode. Yeah, yeah. But that's right. I mean, if that flash escapes out of that channel, which is that detector, and gives signal to the detectors around it, then you've blurred your projection. You've blurred your sampling. That sort of happens at a constant rate. That there will be some bleed of light to the neighbors, right? So 1 photon, 20 photons, whatever, you're going to get a certain percentage bleeds into the neighbors. And yeah. Right. So you really want to minimize it, but you don't want to build a mirror that's so good and so thick that it eliminates your sensitivity to detect photons, right? So there's a trade-off there. So here, each one of these little chips, I might have a picture. Yes, I do. So you lift one off, and it's like 16 by 32, 1 by 1 detectors. A little flash would happen. That flash goes down here to a photodiode, and the signal goes off to the computer. Ring! I've just detected an X-ray, right? And you've got a whole field of these. You can see the kind of picture that you've got there. And we got to plop it back down in there and make our 2D sample array. So now let's look at we've seen something that does sampling. Let's look at the math and how we're going to describe going from a continuous function to a sampled function. And you can imagine that an X-ray shadow itself is essentially a continuous function for what we're concerned about, right? It has individual photons, but for us, we could model that with an absolutely continuous function and not have an error, right? So if we have a continuous function like this, it's the pink line, and we'd like to represent that function with sampled values, we pick our sampling distance, and then we just, sample out the values of that function there, and then that function becomes this thing, right? And this is shown as just a sequence of numbers, right, that are essentially, labeled by n, right? And so the questions are, how finely do you need to sample in order to represent this function adequately, right? What happens if you don't sample finely enough, right? What are the consequences of that? And then the fundamental question that you can ask yourself is, if I have a set of numbers here, right? And I can entirely reconstruct the function that created those numbers. So I can entirely reconstruct this continuous function without error from this finite set of numbers. That's a definition of adequate sampling, right? It's like you've achieved your adequate sampling because you can just reproduce the continuous function, right? And so we'll look at the features of this function that require you to sample at specific rates to achieve that, right? Certain functions you can represent with, like, 3 numbers, right? Or 2 numbers. Like if it's a straight line with a slope, you don't need a lot of samples, right, to represent that. You don't need a lot of numbers, right? But if it's a very complex function as a function in space, you need a lot of samples. And who knows what the most complex function, if I was to just say, okay, now here's f of x. So as I go along in x, tell me what f is that is the function is the most complex to sample and has the highest information content. Does anybody know what that is?
Impulse.
So one guess is I go along 0, 0, 0. There's an impulse, and then I go along 0, 0, 0, right? That has a very wide bandwidth. So to know exactly where that function, or where the function has its position, you need to sample it for infinitely high rate. So, but that function doesn't carry the maximum amount of information. It carries information like it tells you one thing, like where that point is, right? It's an interesting thing. If you ever look at Shannon information theory, I don't know if you've ever worked on that in your EE courses or anything. The function that carries the most information is pixels or values that are completely random point to point, right? So if there's no correlation between each point, right, that is the highest density of information that you can ship with that set of values, right? Because you can imagine, what function could you reduce that down to? So if I have a Gaussian like this, I can reduce it down to the width of the Gaussian, the mean, right, and the height. So I really only need 3 numbers to tell you that everything about that function. If it's a sequence of random numbers, I can't write down a function to tell you what that function is, unless you say, oh, it's the digits of pi. Then you just say, okay, that's one way of saying it, but it doesn't give you, what the next thing was. Okay, so that's our job. Is we have some signal, we want to sample it adequately so we can reconstruct the underlying continuous signal. So here, in MR, we'll go to the time domains and frequency domain, as in seconds and hertz or kilohertz, right? To talk about sampling for a moment here. And this is a very good example for MRI, because the signals that we measure with MRI are radio frequency signals, sort of at 64 megahertz if it's 1.5 Tesla, 128 megahertz RF if it's at 3 Tesla. So it's a signal that kind of looks like this, right? It's an oscillating voltage as a function of time. So we'll sample this at some frequency, and so we're going to call it at basically the sampling frequency. We'll just call it Fs, right? And this gives us the function that we now have in our computer with those points. And this is time. So this is 150 milliseconds here. Here's our function. If we take the Fourier transform of this thing, it will give us the frequency components that are contained inside this function, right? So it'll say, do I have 10 kilohertz in this function? Do I have 5 kilohertz in this function? When you take the Fourier transform, you just go to that. So here's 4 kilohertz. Go up and say, this is the power at 4 kilohertz in this function. And that's what I've got in here. So when you take the Fourier transform, you get a complete spectrum here, and this goes up to 10 kilohertz here, a little bit beyond, and we get this representation of that function. Okay. Now, let's do a little exercise. We'll throw away 7 points and then keep the 8th, and then throw away 7 points and keep the 8th, throw away 7 points, keep the 8th. So take this one and sample every 8th point. So we have reduced our sampling rate now. Those delta functions now have been separated a lot in time. That's a factor of 8 separation, right? And then when we plot that, it looks something like this. So it's hard to tell, right, that it's a lot different, but there's 8 times fewer points here. And then you take the Fourier transform of that thing, okay? What you get is this function. And there's a couple of sort of remarkable features about this one. One is it kind of overlaps with this function close to the origin here. This function looks similar, but then hits a point where it starts just repeating itself, right? It's reflected, and each one of those is just a pure replicant of what came before, right? And this is basically a feature of the discrete Fourier transform and undersampling, which is that when I take the Fourier transform, this thing is going to be periodic. This function is going to be periodic. And the period here is this value, whereas the period up here is actually 8 times bigger, right? Because my sampling here was 8 times higher in frequency, right? Yep.
So the one on the top, and then the difference between the one on the bottom. So if you take less samples, you get a more periodic signal for your Fourier transform.
If my sampling grid here is like every 1 unit, and then I stretch out my sampling grid, so now I'm at every 8 units here, bing, bing, then yes, this thing becomes periodic, or we see the period here compared to up here. The period becomes shorter. Yeah.
So what are you referring to?
Say it again, I'm sorry.
What are you referring to?
Oh, up here with the sampling. Oh, okay. That's in this case, that unit is a delta T. Okay, so it's like, am I sampling every, 10th of a millisecond, right? If I sample every millisecond, then it would be periodic with sort of a kilohertz. 10th of a millisecond, 10 kilohertz. So it's probably somewhere around there, right? And then here, less frequent, right? So this is, the relationship between undersampling and what happens in the Fourier domain, okay? And remember, by the sort of duality of those two spaces, we're going to see it in the other direction as well, right? It'll happen in the other direction. So this undersampling phenomenon can lead to something called aliasing, and that's when these replicants of the Fourier transform get close enough together, they start interfering with your visualization of the function. And here's a very visceral demonstration of what aliasing is. And if I have a clean signal, this is a very clean signal. It's a sine wave that's just going with a certain frequency. Yeah, you have a question?
If at a smaller, like if at a larger sampling frequencies, if at a smaller sampling frequency, you can get the period and then expand it and like resample it. Does that get the above function? Like does that deviate the above function?
No. So once this has happened, once you have undersampled here by this factor of 8 and you create this Fourier transform, this is really as much of the spectrum as you know right here, right? And then the rest is just replicants of that. And there's no way to magically recreate what's out here, right? Because you haven't sampled it. So you just don't know what it is, right?
And sorry.
Yeah,
you
sure.
can also know that the accurate part is the one that you're pointing out because
Yeah.
of the former, or because you know out of the symmetry of the signal that
this is the part that is unique. This part here is also here, and it's also here, and it's also here. Whether or not it's accurate actually depends on the frequency components that were in the original signal. And we'll see that. This can be accurate if there are no frequencies higher than that in the sample, right? It can be accurate even though it replicates itself. However, if there are high frequencies in here that we have missed because we've undersampled it, those high frequencies will alias back into this estimate, right? And your spectrum is distorted. And we'll do an example of that. And that's called aliasing. And another way to describe aliasing is this, where I have a sine wave and I'm going to put a sampling comb to see what's there, right? And so I've got a lot of points for each full cycle of this sine wave. I don't know how many, like 10 points or something along each cycle. So that would seem to adequately sample that sine wave, right? I know where the peaks are. I know the frequency. I could give you the shift, the phase shift, like how the whole thing is shifted in time with that kind of sampling, right? If I drop my sampling again by, say, a factor of 8, like that previous example, then I only get every 8th point. That's what I sample, right? And so when I copy every 8th point down here, so this is the function that's creating the data, I sample that point. And the function's creating the data, I sample that point. Function continues to create the data, and I sample that point. Well, that is also consistent with a sine wave that has much lower frequency. So now I have two ways to produce these data points that I can't distinguish with this sampling. One way is this high frequency sine wave. Another way to produce the exact same points is this low frequency sine wave. And so those two, methods are superimposed on each other. I don't know which one's which when I do this sampling. Which is it? Is it the high frequency one or is it the low frequency one, right? If they're in there. That's called aliasing. That's confusing signals that are actually high frequency signals with lower frequency signals in your field of view. This is a really good example. You've all seen this in your, let me see, how do I get out of here? Sorry. I'm not sure. Oh, there we go. Can I get out of here? Yes, I can. Okay. Let's look at this. This is pretty cool. So this is called the wagon wheel effect. And don't need the music. And while what we're going to see, so the disk is spinning at a constant rate, depending on the frequency of the waves that are in the different circles, you see them spinning at completely different rates, right? And the reason is the camera that is taking this movie is capturing frames at a certain frequency, right? It's coming in at, say, I don't know, 20 frames a second or something like that. And that 20 frames a second is interfering with the frequency that's occurring in this pattern, right? And so you get it completely confused as to what's doing what. Okay. So you've all seen that, I would imagine. Say when you're driving and you look at a car or a truck next to you, and when you're driving along, you look at the wheel of the truck next to you and you see the wheel is slowly rotating backwards, right? Or it's rotating at a different frequency than 55 miles an hour, in that thing, right? What does that indicate? That indicates that your visual system has some kind of sampling rate, right? It's got to have some kind of flickering sampling rate. To see that without a camera being involved or anything like that, it's just your eye brain system is involved. Yeah.
It's like the difference in perceived frequency between like the actual thing and then your like sampling rate on your end.
Correct. Aliasing is the appearance of frequencies that low frequencies are created in your sampling that are actually coming from a higher frequency process. And you can't distinguish that because you haven't sampled fast enough. Okay. If you sampled at 500 frames a second on this thing, you just see the thing going around, right? You wouldn't get this undersampling effect. Okay, let me here. So this, now I forget what this example is about. So there's a chest X-ray here. This is right out of your textbook, so we should all be able to figure this out. Sample is without and with anti-aliasing. Okay, so this has an anti-aliasing filter. This has no anti-aliasing filter. And this is, the original ground truth image. And you can see these sort of hashy structures that come out of here because the digital sampling, the spatial rate of the digital sampling of this thing is aliasing high frequencies that are actually in the image into lower frequencies that come out as these kind of, low noisy bobbles like that. So what you really want to do is filter your data before you sample it with that sampling thing to get rid of that artifact, such that you're going to see a blurrier image, but at least your sampling grid is matched to the frequencies that are coming in and hitting it. Here's another example. I don't know if you can see that, but this, so it's a photograph with two cameras. One's a D60 and one's an SD9. So those of you who are real photo people would know, well, that's the Nikon, that's the Canon or whatever, right? So you're doing a comparison of these two digital cameras. And you take a picture of somebody's coat just sitting on the back of a chair, right? Oops, my bad. And this one produces these waves, right? It looks like there's a source here and there's some kind of wave that's swishing across the field of view, right? And then with this camera, the winner, those things aren't there, right? And so what this is there is an underlying frequency component to the material, to the texture of the material, right? To the weave. So if you look at the weave of the material, it has a specific fundamental frequency or whatever. And there's an interference between the sampling frequency on your detector that's in the camera and the sampling frequency and the actual underlying frequency, right? And it shows up as this low frequency modulation, right? Because the camera can't detect it. It's too high, yeah. It sure is. And we're gonna get there. We're gonna do that. So the other way to do this is with your own cell phone. You can just put it in camera mode and try and take a picture of. You see that monitors are too good nowadays. They're such high frequency. Oh, here we go. Yeah. So if you take any digital monitor, take your camera, just go up to it and go to different distances, and you will see all of a sudden there's this big low frequency interference across the picture. And that's the interaction of this sampling of this thing with the array of pixels on the monitor, right? So that's another demonstration of it. Okay, now we're going to do the math of how you figure this out. You guys, okay. Can you guys still hear me? Okay, and see the slides online because we dropped out a couple weeks ago.
Yeah, we can.
Yeah, we can hear you.
Yeah. Is that a thumbs up? Okay. I know there was like a green flash. Okay. So here's that sequence of delta functions. Okay. And this is the most fundamental one, right? Is that we have a set of integers here. And we're going to call this function comb, a sampling comb, sometimes called an impulse train. Never heard it called bed of nails. That's something Tom calls it, but and so it's basically just a sum of delta functions. Okay, that's what this sum is here. So I've got a whole set of delta functions, and they're displaced by an integer unit n. Okay, yeah, yeah.
The array of the fibers, the picture of your computer is the array of pixels.
Yep.
What's the array that's interfering with the fiber?
With the which image? Oh, like in the it's the discrete digital array that makes the picture. So it has separations in space, and so it has a sampling frequency, right? And as CT does. Digital X-rays, like chest X-rays, the sampling frequency is higher, much higher than what's found in a CT scanner, right? Because you want really high resolution for those pictures. And like when you see a fluoroscopy system and they're injecting that contrast and looking at the vessels, that detector that's underneath the patient is much higher sampling rate than in a CT scanner, right? Okay, so we've got mathematically this thing, which is a comb function. It's important, and I'm going to say this over and over. You'll get tired of me saying this. This is not a sequence of numbers, right? This is a continuous function that's 0, 0, 0, delta, 0, 0, 0, delta. So it's defined everywhere, okay? And it's a continuous function. Okay? You can just as easily make this thing in 2 dimensions just by making 2 indices, right? And giving a separation of delta x and delta y gives you a new continuous function. So it's continuous in x and y. And these are basically parameters of the function, delta x and delta y, right? And so this is just that comb in the plane. Once I set my delta x and delta y, that gives me that 2D comb. Oftentimes when you're using a comb function, you'll want to use it in a normalized way, and that is you bring out the delta x and delta y to normalize sort of samples per unit space, as it were. And it makes it more convenient. So you'll see this often where it's normalized up front. Okay, so here's our comb, which is a continuous function of x, and we have this parameter delta x, which gives us the separation of the delta functions. And why are we doing this? Not even sure why we're doing this. So this is just to show the normalization in 1 dimension. Okay, so to write it, if I have my delta x function here, the thing we're defining is the comb function has a normalization factor out here, and it's x per unit, centimeter, something like that. Okay, so we're going to now sample with our mathematical comb that we have, and it's normalized. Everything's cool. And it's going to give us a continuous function in x that is the version of this thing, which is sampled. Okay, but it's still defined everywhere along x. It's not just a sequence of numbers. And so that's the definition of this guy, the sampled function as a function of x. It's the function itself multiplied by this comb. Okay, and another way of writing this down is I can bring f of x inside the sum, which is the definition of the comb function. And at this point, this thing here, right, is just a sequence of numbers, right? So those are the coefficients that give you, like when you multiply with the delta function, the thing that comes out is the function at this location. And so this is a sequence of numbers. This is a continuous function, right? Okay. And so we have, I'm not sure why I'm doing this. Okay, so that's the point I wanted to make, is the distinction between what is a sequence of numbers that we will actually store on our computer and the continuous function that when you go to prove theorems about how these things behave, you usually use continuous calculus. Okay. Same thing happens in 2 dimensions. Okay, so we have our continuous function in xy. It is the original continuous function multiplied by the 2D delta functions. We can sum that up, and we now have here is the set of discrete values of the function fxy. So one thing we want to, so this is the Fourier transform, right, of the comb function. It turns out it equals a comb function as a function of kx. So this is x in centimeters in space. That's our comb function in space. And I ask, if I take the Fourier transform of that continuous function, right, and ask what is it in the Fourier domain? Well, it's a comb function, and it's, you know, has it's continuous itself, and it is variable kx, and it's, you know, written down like this. So it's just a delta function separated with units. So it's like, it's not that intuitive, right? If you have a comb function, you think, wow, there's very high frequencies in every single one of those delta functions, right? So my Fourier transform probably has high frequencies in it, right? So I know it's going to go out to infinity if it's a delta function. Remember, the Fourier transform of a single delta function was a constant, right? It was just 1 everywhere. Every frequency was in there equally. Now what we're saying is I have a delta function, and then it has all of these replicants, right? That actual transform is a set of replicated delta functions in the Fourier domain. Yeah. Exactly. That's exactly what it is. So it's in cycles per centimeter, cycles per millimeter. Yep. Okay. And from scaling, we know if this is our original function, was fxy, and then we multiply x by a, and we multiply y by b, and so we scale the axes of fxy. What happens to the Fourier transform? Well, we know it scales, but in the inverse way. Okay, so if this a is 2, then this is 1/2, and it gets normalized by a times b. Okay, and so the Fourier transform of this thing turns out to be this guy, okay, which has the scaling factor up front, and it has discrete n that are in units of 1/x. So that's the, you know, this is the continuous variable kx. The delta functions occur at these values of kx, right, as we go up through n. Yeah.
So it's almost like the same signal in like the time domain, except just like with smaller amplitude and like less weight between each thing.
Yeah, interestingly, that's exactly right, in that if my time, let's call this, I mean, it's x, so it's spatial domain, and this is spatial frequency domain. So spatial domain, I have some frequency of delta functions, you know, like delta functions per unit space, right? And then when I go into here, I have 1 over that frequency of separations of my delta functions, right? And if I put these ones closer together, these ones get farther apart, right? So as my sampling comb gets closer and closer together, and the delta functions come closer and closer together using this, right? So now delta x is bigger and bigger, right? Then these get farther and farther apart in the Fourier domain, right? And that's the essence of aliasing, is that these delta functions, the separation of these delta functions, I really want to make them in the Fourier domain far enough apart that the actual frequency content of my signal doesn't overlap with multiple delta functions in the Fourier domain. It just stays inside one of those blocks, right? We'll see that. So here's our comb function, delta x. Comb function in the Fourier domain, 1 over delta x is the period of those. As delta x gets smaller, this is going to get wider, farther apart. Right? So here is the Fourier transform of my sampled function. So I have g of x is a continuous function here, right? I sample it with my comb that has this spacing delta x, right? And take the Fourier transform of that whole thing, right? Then I can bring out, right, the Fourier transform here through the convolution theorem. Remember, this function times this function, right? So when I have multiplication of two functions, I take the Fourier transform of that. In the Fourier domain, that's a convolution of the individual functions. So I take the Fourier transform of g, write it here, and I convolve it with the Fourier transform of the comb function, right here. So we're getting to the Fourier transform of this sampled version of our underlying signal. And then I can replace, using what we've done in the previous section, the Fourier transform of the comb function turned out to be this, right, from the last slide, and I'm convolving it with this, right? So now you can imagine I can bring this out, bring the convolution inside the sum because it doesn't affect it. And so now I'm convolving g of x with this set of delta functions who are replicated at this frequency here, right? And so what that does is it sifts out the values of the Fourier transform of g here such that we get a continuous variable here, but the actual value of the Fourier transform at any point, so if I have some value of kx, at any point kx, it's the sum of the Fourier transform of this guy, of the original function, evaluated at replicants along the frequency dimension, okay? So here I have n is going from -infinity to infinity, and I basically take the value at any point kx, and then I add to it the value of gx separated by 1 over delta x. Then I add to it again, separated by 2 over delta x. Then I add to it again, separated by 3 over delta x. So every point in the Fourier transform of this sampled function is an infinite sum of values that are in the Fourier space. So ideally, you would like it such that when you're doing this summation, the value of the Fourier transform of g, of capital G, at gx minus 1 over delta x, you would like that value to be 0, right? And that way, this sum really only has one component, and it's this at kx. It doesn't, when you do this addition, it doesn't add any more components, right? And so graphically, you can look at it this way and say, here's my Fourier transform of this guy, which is it's this sampled, it's not the continuous version of gx, it's gx multiplied by those delta functions. And this is its Fourier transform here, capital G at wave number kx, right? If when I look at my sampling train, over here is separated by delta x, and I go to 1 over delta x, if these are the values, so let's look at this one first. So this is, g sub s of kx out to some value here, which is like 1/2 of 1 over delta x. And then I look at the values of g of x replicated, around here. If this falls off such that when I sum those together to get this, this is a good representation of the Fourier transform of this function, right? If on the other hand, let me see, if on the other hand, I have this function to begin with, and I set my delta x such that the replicants now move in, that means I sample with lower frequency, my sample points move apart, right? Now, in the Fourier domain, these replicants move closer together and they start to overlap so that the bandwidth of this function, right, starts overlapping with its next replicant. And so I get corrupted values in here, right? Because these sums don't go to zero. Yeah?
The maximum component in the frequency domain?
Yeah. So that's it. If I look at the bandwidth of my system, it is, in this slide, we're just calling that U. And then all frequencies, for all wave numbers outside there, this G function is zero, right? That's where we're going with this. But let's go back one, okay? And we'll say the Nyquist condition to avoid aliasing, to avoid that overlap. If my bandwidth of my function is this, it's plus or minus, or it's negative U to U, and that's my total bandwidth of the function that I'm trying to sample, right? If I sample adequately, I will separate these things by, 2U here, right? And so that tells me how far apart those samples should be, right? So this KS, right, this thing should be greater than 2U, right, to keep these things apart. And that's for a function that is band limited. That's the Nyquist criteria. If you don't make that happen, if it's less than 2U, then you start getting these overlaps. And that's what aliasing looks like. Mathematically, this is what it looks like. What you saw in the example, right, was essentially lower frequencies looking like they're there, and they've been actually, where they're from is the summation of a higher frequency that was undersampled, right? So that higher frequency folds back in and you see it as a lower frequency. In 2 dimensions, same thing. This is the Fourier space, the Fourier transform of a continuous function fxy. And then here's the domain over which I have frequency values for that function, right? So we say it's band limited. It doesn't have any higher frequencies than we see in this ellipse. We can set a sampling grid such that when we look, at sampling that function and taking the Fourier transform of those samples, we are separated from all of these replicants. And so this is a clean representation of that band limited function. It's inside that box. Undersampling, they're all going to start overlapping. Right? So just as a gestalt, if I'm looking at this sine wave and saying, well, what is the frequency, just in raw numbers, that I need to sample this sine wave adequately, right? So let's say that it's oscillating at 1 cycle per millimeter. So as I go through a millimeter, it makes 1 cycle here, right? And so where should I sample this thing to make sure that I'm adequately sampled, do you think? Just guess, right? Obviously, I've got a lot of samples here. I've got 10 samples, and I don't need 10 probably to tell you what the frequency of that sine wave is. Yeah. One at the top, one at the bottom. Yep. That'll get you there, right? And so that means you need basically 2 samples per wavelength, right? So that's where that 2U comes from. I have a wavelength of, say, 1 cycle per millimeter. I need 2 samples across that in order to get the top and the bottom of a sine wave, right? And if I don't do that, if I do something like down here, then I'm going to see this artifactual fold over of signal. And here's a graphical demonstration of that. So here, this is space along this axis. So I'm going from 0 to say 5 centimeters. And I have 1, 2, 3, 4, 5 cycles. So 1 cycle per centimeter in this wave here. And this essentially it's a, you can encode this with one number, right? This is the wave number. It's 1 cycle per centimeter. That tells you the whole function, right? That's all we've got right now. We're going to sample it every 10th of a centimeter. And so we'll get 10 pixels across each phase of each 2 pi phase of the sine waves, or across here. And this is what the picture looks like. So it looks like a nice plane wave, right? If we drop every other sample, so now we're going to sample that sine wave at 0.2 centimeter intervals, right? So I'm going to get 5 samples per wavelength. This function is what we get. And you look at it, you go, huh, it's sort of got a very discrete, steppy kind of look to it, but it's still a good representation of that sine wave, right? Of the frequency kx1. If I go to 0.3, I look at this, I still have a relatively periodic high frequency signal here. It's starting to look a little messy, but like there are other periods that are occurring, like here, right? But still the main frequency is there. If I go to 0.4, right, I get something that looks like this. And so now my representation of the frequency doesn't look great. This is 0.5, and I have 1 up, 1 down, 1 up, 1 down, 1 up, 1 down. And so this is the sort of lowest sampling frequency I can use in order to reconstruct this sine wave well. Once we get to 0.6, this is what it looks like, 0.7, 0.8, and then 0.9, we start to see this really low frequency stuff folding back in. And you can play around with this in MATLAB and stuff like that in terms of sampling. So in this case, our U value for the limit, or the band limit of the signal, was simple. This is millimeters, 1 cycle per millimeter. So the smallest spatial period is 1 millimeter. Therefore, I need delta x to be 1 over 2u, which is 0.5 millimeters. Okay, that's called the Nyquist criterion. Okay, and if I have those frequencies in my signal, I should sample at that rate, right? So in CT, we have a fixed detector array, right? So the delta x and delta y of that, when we go back to the comb function, that's been set, right? We can't really change that with a switch on the scanner. It's just what we've got. And so the question is, if you have frequencies in there that are higher than 1 over 2 delta x, 1 over 2 delta y, what can you do? And one thing you can do is, if you have that continuous image, you can filter it, right? And you filter out the high frequencies before it hits your detector. And that way you will avoid aliasing, right? The issue is you get a blurry picture, but it's matched to your sampling rate, yeah?
Generally, the signal would compare of multiple frequencies, like because Fourier transform.
Correct.
Do we need like the highest frequency?
Yes. Yes. So that's what if we go back to this diagram, the question is, what frequencies are required? And saying that something is band limited means when I look at little g of x and I look at all those squiggles and stuff and sine waves, this is the highest one that's in there, this boundary here, right? And so that could be 1 cycle per millimeter, 50 cycles per millimeter, but it's some kind of boundary that says above that, I don't have any other signals in there. Well, a band limited signal. And so you can make a filter to band limit your signal before it goes into your detector electronics. And this is done a lot in MR, right? Where you actually filter out high frequencies that you don't want to sample, right? And one way of doing that filtering, this is not a good or a well-behaved filter, but it's easy to understand. And that is, if I have a time domain signal or a signal in space, and I want to band limit it, let's look back at our dictionary of Fourier transforms that we have. Remember, we had a square wave, looks like this, and its Fourier transform looked like this. It was a sinc function, right? So if I want to band limit a function, i.e., I don't want, if I flip, yeah, let's flip the direction. So by duality, remember, you can go Fourier transform one way or the other. Let's set this to kx, and this is now x, right? Same thing. But what I'd like to do is limit my signal so that I don't have any features of frequencies higher than this, right? So what I can do in the X domain is I can take this and I could convolve my signal with this. And it's a filter, right? So it basically blurs neighboring pixels together to give you a sum with these weights. And then all of these frequencies are gone, right, in that signal. And so then you could sample that. And you know it's inside there. The issue with that is it's not, rectangle filters aren't that well behaved. Usually you try and pick something such that you get a smoother roll off and the derivatives are nice and things like that. Corners are not the best, but that's how you would potentially filter down a signal such that it was inside your bandwidth of your detector. Okay, so that's it basically for signal processing. We're 12:06. Any last questions on that? Yeah.
Also, could you go back to the showing the picture with the aliasing?
The code?
The sine wave and aliasing.
Oh yeah, sure. Oh, I think I know what you mean. This guy?
Oh, before that.
This one. Yeah.
Guy. So we mentioned that if we sample top, one at the top and one at the bottom, we
Mhm.
have aliasing. But like some accidentally we get the like middle point.
You get the middle point. I don't know what that means.
Like we sample the middle points. Oh, if we like point to the top.
Okay, up here,
Yeah. If we sample that middle point and the right middle point.
like here and
Yeah,
here.
here and
Yeah,
here.
yeah.
And then it goes on.
Oh, just sample here. Yeah,
Isn't that alias?
it is. And what's it aliased with? It's your high, say this is the limit, our band limit. For that sampling, that would be the band limit, right? We're getting 2 samples per cycle, right? But that band limit also corresponds to what's happening at the average, at DC, at 0 frequency, right? So that's the point at which that occurs, that overlap occurs, right? Yeah. So that, I mean, you want to be greater than that sampling rate, right? In order such that you start to get some kind of change. Okay.
So that's the threshold.
Yeah. That's a good point. And this is actually something you can fool around in MATLAB with and see what, practically speaking, we're always using these sample delta functions, right? Because we have a sequence of numbers as our data, right? So there's sampling in all of the data we use. So you can make a function, sample it in MATLAB, take the Fourier transform, and see what kind of artifacts show up, in the function. Okay, so we got 12 minutes. So I'm going to start getting going on CT here. Okay. if you want to get started so you can start thinking about your projects, etc. So here's the scanner. Okay, we're pretty familiar with it now. You know, there's a tube in here, there's a detector over here. Both those things spin around at high velocity. They spin around now like greater than 4 times a second. Okay, the thing. That means the electronics in there it has sustained like 80 Gs, right? So you have to tighten your bolts, right, to get that thing to behave well. This guy looks like he's going to get his chest scanned. The tech is putting on ECG leads so that you can trigger your acquisition to the heart rate. So physiologically, if you want to see something about the heart, you get that signal and you say, okay, scan at this time with respect to the heart rate. This tech is loading up a line of contrast, and this is a very precise plunger that will inject the contrast into your vein at a really specific rate, like say 5 cc's per second. I'll just put it in there at that rate. And the table is actually a pretty high precision unit. It probably is accurate down to about 1/10 of a millimeter. Like when you push something in, take a picture, take it out, push it back in, it's reproducible to sort of 1/10 millimeter or something like that. It's really good. It also is very reproducible in terms of the rate of travel, because there'll be scanning modes where we push the patient through the scanner continuously while the detector and sampling thing are rotating. We'll just take continuous data along a helix, right? Which is really cool, really fast way to scan. Here's modern brain scans out of one of these machines. It's not first in the first that was done. This is an acronym for a really detailed way of doing reconstruction to compensate for the fact you have bone here absorbing a lot of x-rays, etc. So it uses a really high definition model of x-rays and how they move through the object, but it's very expensive. Here is using that same reconstruction method after injecting contrast into the vessels, right? And so you get ridiculous high spatial resolution in the head, beautiful images of, the cardiovascular system. These are all after you inject the contrast, you push the patient through the scanner and inject while the contrast is moving down in their body. So this whole thing is usually done in under a second, right? So all of those images are taken. Here's image of somebody who has 2 hip implants, and the metal absorbs virtually all the x-rays on these projection lines. So you get these huge artifacts, but using modern reconstruction techniques, you ignore these views and just reconstruct using the surrounding views, and you get rid of that artifact. Yeah.
So let's say with a patient with AFib, where
Yeah.
the heart rate is irregular, are they able to compensate for that if it's not like regularly irregular?
Yeah, exactly. So if you're in atrial fibrillation, your heart doesn't reproduce an R to R interval, which is sort of constant. And under those conditions, CT is great because you can take your image inside one heartbeat. So basically, you just get a trigger, and I don't really care when the next one's happening or when the previous one happened. I get a trigger and I just image. And so under those conditions, I get a good picture. MR, you usually need 16 to 24 to 48 heartbeats. And you take data on each heartbeat and you assume that each heartbeat produces the same motions. And so people in AFib produce images that have crazy artifacts, and you have to compensate for those. Talking about the heart, here's CT images of, the heart. The voxel sizes here, like 0.5 by 0.5 by 0.5, something like that. Really high resolution voxels. You can then cut the volume in any, orientation you want to look through for specific things. Here's a 150, 170 milliseconds worth of data made this heart. So if this person was in AFib, you don't care. 150 milliseconds, you just got it in one heartbeat. But the acquisition was delayed after the injection until the contrast got down into all the coronaries. So you have to time that well. So when you inject, it's usually like between 12 and 25 seconds to get all of the blood down into the coronaries, depending on how your heart's going. But in the end, you can make these totally spectacular images of coronary vessels to determine if a person has heart disease. And so they show up at the ER, say, and they have chest pain and classic symptoms of having a coronary problem or a heart attack. You put them in this scanner, and if their images come out like this, which 50% of the time they do for people in the ER that have chest pain, you say, well, here's some Rolaids, go home. You're not going to die of a heart attack, right? And that is done now in Europe. CT is done first order of business. Somebody shows up in Britain with chest pain, the first thing they do is a cardiac CT, right? In their workup. In the United States, that is not done, right? And the reason it's not done is ironic. It's because this imaging modality is too cheap. Just let that settle in for a second, right? It's too inexpensive, right? And so in an environment where you make money by doing procedures, you'd rather do the technique that you can charge 3 times for, which is like nuclear medicine. And it sucks, right? So economics pushes people to these terrible, like non-optimal imaging protocols, right? And but now that you've taken this class, if your parents or somebody has chest pain and they're going to the hospital, you tell them, you get a CT, get a cardiac CT, right? Because it's the best way to diagnose it. And it's been shown in many tests and everything like that, it is. So in Europe, because it's every procedure is a cost to centralized healthcare, they like the fact that it doesn't cost as much, right? Here, it just don't make as much profit. So here you can then keep the CT scanner going for the whole heartbeat. So trigger and then image across the whole heartbeat instead of just a window of 170 milliseconds. Say we image over the whole second, and then we make sequential CT images, and then you play those CT images back on a computer. It looks like this, right? Which is spectacular, right? This is in one heartbeat. You get this movie. And you can see that essentially the contraction of the left atrium, then contraction of the left atrial appendage, not going to see that anywhere else, right? And the left ventricle going, et cetera, et cetera. So spectacular way to make pictures of the heart, yeah? It's already been in the right ventricle. It's a small temporal bolus of contrast, and it passes through the right ventricle. And so you could image the right ventricle at that time, which would be like 8 seconds earlier, right? And then it goes off to the lungs, and it comes back into the left ventricle and into the left atrium. Timing. It's all timing. If I'd waited 10 more seconds, all that contrast would be gone, right? Yeah.
Imagine now if you were wanted to detect irregularities in your heartbeat, then you would probably image more than one heartbeat, or would you then go over to MR because the dose gets too high?
No, you can. We have a protocol now, a research protocol, where we take 27 images and we watch where the contrast goes, because sometimes the contrast pools in various places, which is very dangerous. And so you basically want to evaluate, is this person at super high risk for throwing a thrombus and having a stroke? And so we take very low dose pictures, but over the course of 40 seconds, and we see where all the contrast goes, how long it stays there, right? And model that with equations and say, look, there's a chunk of the left atrial appendage in this patient that the contrast goes there and stays. And that's bad, because you don't want it, just staying there and being viscous and then throwing a thrombus. So it's a trade-off between dose and how many pictures you want to take. You want the total dose to be about the same, right? So if you're looking for highly detailed coronary artery images, then the dose goes up. Are we out of time? Oh, 2 more minutes. So I did MR, cardiac MR for 25 years or something like that. Like, was in cardiac MR when the field started, and love it. It's great, and you'll see some amazing pictures. But CT is just blows it out of the water for spatial resolution and time resolution and just ease of doing it. Just putting a patient in and getting it done. It's way easier. There's a course in the spring, 280C, that we give, in which we look at all these imaging modalities in the heart, because cardiac imaging it's a great challenge, right? The brain, it just sits there. You just sit there. You can have somebody sit in their brain like minutes. It doesn't matter, right? You can lock them down. fMRI is fun though. But the heart, I mean, it's going all over. They're breathing, so you have to be really clever about how you get the pictures done. And that's what we'll start next time. We'll start about how the CT acquisition occurs.